This is lesson 5 from the Trig 2 Identities unit, and it's on page 625 of the student workbook. What this entire lesson is going to be on essentially is we're going to continue with looking at identities and proving identities, but more specifically we're going to be focusing on restrictions and on NPVs. And remember that you can never divide by 0, right? So you cannot divide by 0. So whenever we have fractions, we can't have 0 on the bottom. That's going to give us our NPV or our restriction. So flip over to the next page, page 625. Where we have non-permissible values for an identity is when we have tangent, cotangent, secant, and cosecant functions. All of these functions are going to have NPVs. So why would, for example, tan have an NPV? The reason why tan has an NPV is because tan of x, the quotient identity for tan of x is equal to the sine of x over the cos of x. And we know from non-permissible values that the cos of x could never be equal to 0. So my restriction, or the non-permissible value, is when is cos of x equal to 0? And my restrictions are essentially that cos of x cannot be equal to 0. So if I was to look at my unit circle, where is x equal to 0? So cos, remember, are your x values, and we cannot have this would be a restriction and this would be a restriction. So essentially cos of x cannot be equal to pi over 2 and to 3 pi over 2, right? Cotangent. So the identity for cotangent is cos over sine. And cosecant is 1 over sine. So for both of these, the non-permissible values are when sine of x equal to 0, and we know that sine of x cannot be equal to 0. So where is sine of x equal to 0? Sine of x is equal to 0, at pi, and then back at 2 pi, right? So we'll talk about how we're going to write these restrictions. The bottom of the page, I sort of want you to star this. This is going to give hints on proving an identity. The book suggests to start with the most complex side, though what you'll actually see is that sometimes I'll look at the simpler side first, just to make sure to see if that could be rewritten, and then I go to the complex side. If possible, we're going to be using our reciprocal, quotient, or Pythagorean identities. Number 3, I find super important. If necessary, change all trig ratios to sine and cosine. So when I do an identity, or when I'm proving an identity, if I see tan, I immediately will change that to sine of x over cos of x, right? I want my primary trig ratios specifically sine and cosine. So if I saw secant of x, right away I would change that to the identity of 1 over cos of x, the reciprocal identity. Then we're going to look for factoring. So we're going to factor where possible. And then if there's a sum or difference of fractions, so if you're adding or subtracting fractions, what we need to do is combine as a single fraction. So this is where we're going to be dealing with common denominators. Okay? And you'll see all of these in the next few examples. Okay, so class example 1. Consider the statement 1 over cos of x minus cos of x is equal to sine of x tan of x. Verify the statement is true for x is equal to pi over 3. So just going back to our unit circle, if we were doing that counting method, remember that pi over 3 is the same thing as 2 pi over 6. So where on my unit circle is 2 pi over 6? Here's 1 pi over 6, 2 pi over 6. Remember, this is 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, so that's pi. But 2 pi over 6 would be right here. So that's 2 pi over 6, which is pi over 3. And remember that's essentially 60 degrees. So on my unit circle, the coordinates at pi over 3 are 1/2 and root 3 over 2. Right? So I'm always going to write that's my x value, that's my cos value, this is my y value, which is my sine value. And then what I'm actually going to do, because I know this question is going to ask for it, let's calculate the tan at pi over 3. So tan at pi over 3, tan is y over x. Y is root 3 over 2. And I'm going to multiply it by the reciprocal of 1 over 2, which is 2 over 1. So the tan of pi over 3, or sorry, the tan of pi over 3 is root 3. Okay, verify. So left-hand side versus right-hand side. Remember, I always do my dividing line. And I'm just going to rewrite my identity. So this would be the left-hand side of my identity, and this would be the right-hand side. So 1 over the cos of x minus the cos of x is my left-hand side. My right-hand side is sine of x over tan of x. From here, they want me to verify this statement is true for x is equal to pi over 3. So take x out and substitute in pi over 3. 1 over the cos of pi over 3 minus the cos of pi over 3. On the right-hand side, I'm going to have the sine of pi over 3 times the tan of pi over 3. Okay. When we're verifying an identity or verifying something is true for a given value, we don't need to worry about which side we start with. So starting with the most complex side, I don't need to worry about because I'm going to be plugging in x is equal to pi over 3 to both of these. Now, 1 over cos of pi over 3. So cos at pi over 3 is 1/2. So that would be 1 over 1/2 minus the cos of pi over 3. Remember, cos of pi over 3 is 1/2. 1 divided by 1/2. So 1 divided by 1/2 is the same thing as 1 times 2 over 1. So 1 divided by 1/2 would be 2 minus 1/2. Let's get common denominators. So we have fractions. So this is 2 over 1. I need a common denominator of 2. So I'm going to multiply this side by 2 and this side by 2. And I have 4 minus 1. So on the left-hand side, I've got 3 over 2 is what I get on the left-hand side. And let's see if I get the exact same thing on the right-hand side. So on the right-hand side, sine of pi over 3. So sine, remember, is your y value. So root 3 over 2 times the tan of pi over 3. Tan of pi over 3 is root 3 over 1. Root 3 times root 3 is just 3. 2 times 1 is 2. And what I've essentially done is I verified that this statement is true when x is equal to pi over 3. And I have left-hand side, which is equal to right-hand side. Okay. Now what we're going to do for C is we're going to prove this statement is an identity using an algebraic approach. Okay, so what I want everybody to do is rewrite the left-hand side and the right-hand side, and then we'll use our quotient law and any of the identities to prove this. So on the left-hand side, I have 1 over cos of x minus the cos of x. And on the right-hand side, it was sine of x over times tan of x. Now, it says to start with the most complex side, which would be this side here. But what I do is I say, okay, sine of x times tan of x. I'm going to change tan of x, because remember that, which point was it that said, if necessary, change all trig ratios to sine and cosine? So scanning this question, right away, I want to change this, right? So I would say, okay, the right-hand side is sine of x. Tan of x is sine of x over cos of x. Two fractions, write them together as one fraction. So sine of x times sine of x is sine squared of x over cos of x. So when I do my left-hand side, the goal is to either get to this point here, sine of x, tan of x, or I need to get this on the left-hand side. And then what I've done was I've proven my identity using an algebraic approach. Okay, so fractions, right? Let's deal with fractions over here. So this cos of x is over 1, and I need to get common denominator. So I have cos of x over here. I need a cos of x over here. So I'm going to multiply my second fraction by cos of x, and this side by cos of x. Now my denominator is cos of x, and my numerator is 1 minus, this becomes cos squared of x. What you need to clue in is whenever you see a squared, say to yourself, is this a Pythagorean identity? And you'd bring out your formula sheet and you would look at the Pythagorean identities and see if this matches with one. And this would be a Pythagorean identity. So the Pythagorean identity is sine squared of x plus cos squared of x is equal to 1. That was the identity. If you see sine squared of x plus cos squared of x, you could take this out and you could put in 1. Look at this identity and say to yourself, how did they get 1 minus cos squared of x? So here's my 1 on the right-hand side. If I subtract cos squared of x and subtract cos squared of x, now I have this 1 minus cos squared of x. And what is this equal to? 1 minus cos squared of x can be rewritten as sine squared of x. So the identity to replace 1 minus cos squared of x is sine squared x. And the denominator is cos of x. And if you look, left-hand side equals right-hand side. I have just proven my identity. So left-hand side is equal to right-hand side, and my identity is done. Okay, B says use a graphing calculator to show that the statement is probably an identity. So if you were to do B, what you are doing, and I'm not going to graph it for you, but you could if you want to check this out. On the right-hand side of the equal sign, you could punch this into y1 on your calculator, and on the left-hand side, y2. And if y1 is equal to y2, the graphs are going to be identical. Okay, so we won't do B. And I'm not going to assign any calculator questions for the homework. I just want you to be very comfortable with proving an identity, verifying given a number, so like verify given pi over 3, and then D. I want you to be, at the end of this lesson, very comfortable with doing D. So state the restrictions in terms of X. Okay, how do we do restrictions? So restrictions, remember, we could never divide by 0. So what you need to do is you need to look at your algebra and you need to say to yourself, where are you dividing by 0? And where we're dividing by 0 is right here. So cos of x could not be equal to 0. And then on the left-hand side as well, it's going to be the same thing, right? They have 1 over cos of x. I can't have this be 0 because I can't divide 1 by 0. So my restriction is only cos of x cannot be equal to 0. Okay? So cos of x could not be equal to 0. So then what I need to do is I need to go to my unit circle and I need to say, okay, well, where are all of the points where cos of x is equal to 0? So I'm going to look at all of my x values on my unit circle. And cos of x is equal to 0 over here, which is at pi over 2, and over here, which is at 270 degrees, which is 3 pi over 2. So how do I write essentially that, okay, x cannot be equal to pi over 2 or to 3 pi over 2? Right? Those are my restrictions, but I want to write it as a general solution. So what I hope everybody sort of sees is that you always state your smallest restriction first, which would be pi over 2. And then what do I have to add in order to get to 3 pi over 2? And what I'm adding is pi radians, right? If I go from pi over 2 and I add pi, I get to 3 pi over 2. And from here, if I add pi, again, I would get back over to this coordinate here. So my overall restriction, how I'm going to write this, what the solution would be, it would be pi over 2 plus pi n, and n belongs to the set of integers, because remember that we could go in the clockwise direction or in the counterclockwise direction. So that would be the restriction there. Okay, let's look at class example 2. So sine of x over cos squared of x plus sine 3 of x is equal to 1 over cosecant of x. So we're going to verify this algebraically, and we're going to determine the non-permissible values. So in order to do this, let's write our left-hand side and right-hand side. So right-hand side is 1 over cosecant of x, and left-hand side, it looks really crazy, but you'll see how nicely this is going to clean up, is sine of x cos squared of x plus sine cubed of x. Okay, again, the book sort of recommends always starting on the most complex side, which is the left-hand side. However, I like to look at this and say to myself, okay, what could this become? Like, how could I rewrite this right-hand side, which is the simpler side? So cosecant of x, the identity for this is 1 over sine of x. So this becomes 1 over 1 divided by the sine of x. And 1 divided by 1 over the sine of x is the same thing as 1 times the sine of x over 1. So this entire identity, what it simplifies to become is the sine of x. And the reason why I write that is because now on the left-hand side, my goal is to either get to this 1 over cosecant of x, or I know that 1 over cosecant of x is the same thing as sine of x. So I need to get my left-hand side to be equal to either 1 over cosecant of x or the sine of x. Now, I don't have any identities in here like tan or cotan that I could rewrite in terms of sine and cos. So what I'm going to be doing is I'm going to be saying, okay, is there anything that I could factor in here? If you have a sine of x and a sine cubed over here, what I could factor out from each of those fractions is the sine of x. So whatever you factor out goes in front of your bracket, and your answer goes in the bracket. So that would give me cos squared of x plus sine squared of x. Okay, this is nice and clean. And look at this, cos squared of x plus sine squared of x. Whenever you see squares, look at your Pythagorean identities and say, is this a Pythagorean identity? And we actually did this identity in the previous question. I wrote it down here. Sine squared of x plus cos squared of x is equal to 1. So what can I do? I could say this is the same thing as writing 1 times the sine of x. 1 times the sine of x is simply the sine of x. So I hope that everybody's seeing left-hand side is equal to right-hand side. So left-hand side is equal to right-hand side. And what I've done is I have proven that identity. Okay, let's look at the second part of this question. So the first part was just proving the identity using algebra, and the second part was determining the non-permissible values. So remember that non-permissible values, we could never divide by 0. So essentially, this here, cosecant of x, could not be equal to 0, right? I cannot have 0 here. So cosecant of x could not be equal to 0. So we know that the cosecant of x is equal to 1 over the sine of x. So essentially now, the sine of x could not be equal to 0, right? I can't have 0 here. And cosecant is the same thing as 1 over sine. So I can't have divide by 0 over here. So my restriction is that the sine of x cannot be equal to 0. So looking at the unit circle, 1 comma 0, 0 comma 1, negative 1 comma 0, 0 comma negative 1. So we're dealing with sine of x cannot be equal to 0. So that is my y values. So where is y equal to 0? at 0, and then if I add pi, I would get over here on the unit circle. If I add pi again, I get back to 2 pi. So how do we write this as a general solution, knowing that I can't ever be at 0, at pi, or at 2 pi? My x cannot be equal to, so instead of saying 0, we start at pi plus pi n, right? So my restriction, sine cannot be equal to pi, and I either add pi or subtract pi to write my general solution, and x belongs to the set of not real numbers. X belongs to the set of integers. And that would be class example number 2. For class example number 3, so this one I would say is probably the most complex one. Again, I am going to start on 1 over cotan of A, and I'm just going to say my left-hand side, I either want to get to 1 over cotan of A, or what is 1 over cotan of A? So cotan, remember, is the cos of A over the sine of A. So that's 1 divided by the cos of A over the sine of A. And 1 divided by this is the same thing as 1 times the reciprocal. So the reciprocal of the cos of A over sine of A is going to be sine of A over cos of A. So for the left-hand side, I either want to get that answer or this answer, right? Either one. Okay, sine of A plus the tan of A. So let's take out tan of A, and we always rewrite those in either sine or cosine. So sine of A plus tan of A is the sine of A over the cos of A, all over 1 plus the cos of A. In my numerator, we've got 2 fractions, and they say if you've got fractions and you're adding or subtracting fractions, you need to combine these fractions. So put this over 1, and I need to get a common denominator of cos of A. So I'm going to multiply this by cos of A and this by the cos of A. Now what I have is cos of A, sine of A plus sine of A. Cos of A, sine of A plus sine of A, all over, the denominator here is the cos of A, and this is all over 1 plus the cos of A. Okay, this is what we're going to need to clean up. So if I just gave you that fraction on its own, and I said, how could you clean this up? What you need to see is that the sine of A and the sine of A could be factored out, right? I could divide out a sine of A here and a sine of A here. So I need everybody to do that. So this becomes, if I factor out a sine of A, it becomes, what do I get? Cos of A plus 1 all over the cos of A. And this is being divided by this guy here. But what I'm going to do is, instead of dividing by this fraction, I'm going to multiply it by the reciprocal, right? So I'm going to take this first fraction and I'm going to multiply it by the reciprocal. And to turn this into a fraction, I'm just going to put it over 1. And so the reciprocal would be 1 over 1 plus cos of A. What you should see when we multiply fractions, if I put this in a bracket, is that the cos of A plus 1 and the 1 plus a cos of A, these are identical. And because we're multiplying, I could cancel the numerator and this denominator. So this would cancel with this. And what I would be left with is the sine of A over the cos of A. And I could stop there because I've now proven it. Sine of A is equal to cos of A. If I really wanted to, I could say that the sine of A over cos of A um, like convert that back into 1 over cotan of A, but really left-hand side is equal to right-hand side. I'm going to stop. So left-hand side is equal to right-hand side. That concludes class example 3A, so proving the identity algebraically. Let's look at B and the non-permissible values. So the non-permissible values, if I go, so just let me have a quick look here. I just want to make sure I did this correctly. So 1 over cotan of A is cos of A over sine of A, and that becomes sine of A over cos of A. Okay, so let's look at what all of our denominators, and they can't be equal to 0. So on the right-hand side, I am going to have cos of A could not be equal to 0. That's going to be for B, one of my non-permissible values. I have to figure out wherever cos of A is equal to 0. If I go over here, okay, and I look at my fractions over here, where are we going to get 0? So what I need everybody to sort of see is that this fraction here can also not be equal to 0, right? So 1 plus the cos of A cannot be equal to 0. Therefore, cos of A cannot be equal to -1. So this guy cannot be 0. This denominator cannot be 0. And where this denominator is 0 is when cos of A is equal to -1. So I just subtracted 1 from both sides of the equation. So I'm going to find all my values where cos of A is 0, all of my values where cos of A is -1. And then my last non-permissible value is in this equation here. When I rewrote cotan of A was cos of A over sine of A. So neither of these can be 0, right? Because if either of these are 0, I'd be dividing 1 by 0, which I can't do. I've already taken care of cos of A cannot be 0 here, but my last non-permissible has to be, well, the sine of A can also not be equal to 0. So now I'm finding, okay, well, where's the sine of A equals to 0? Where's the cos of A equal to -1? And where is cos of A equal to 0? These are all going to be non-permissible values. Okay, so where cos of A is equal to 0 is, so we'll start with that guy. Cos of A is equal to 0. A cannot be equal to, so let's find out where x is 0. Pi over 2 and 3 pi over 2, right? So pi over 2 and 3 pi over 2, A cannot be equal to pi over 2 plus pi n, and n belongs to the set of integers. Next, I'm going to go over where cos of A is equal to -1. So where is x equal to -1? And that would be right here, and that's at pi. So that restriction would be A cannot be equal to pi plus pi n. N belongs to the set of integers. Okay, so we can't have pi. Actually, that's incorrect, because if I want, so let me think about this for a second. If we can't have pi, the next time I would get to pi is actually by adding 2 pi. So x cannot be equal to pi plus that should be 2 pi n, right? Because we can't have pi and then I can't have 3 pi, I can't have 5 pi, or I can't have pi and subtracting 2 pi. So that would be my restriction there. And then the last restriction, what did we say it was? So the last restriction was when sine was equal to 0. So where are all of my y values equal to 0? So that would be here and here. Okay, So that restriction, a cannot be equal to 0, pi, 2 pi, 3 pi, 4 pi. How do we write that? So we would say for the sine of a can't be equal to 0, you could sort of write it in two ways. You could say it cannot be equal to pi plus pi n belongs to the set of integers. Another way that this could be written is the same thing as just saying pi n, right? N belongs to the set of integers. Because what you're saying is a cannot be equal to pi, which is right over here. And every time we add pi or subtract pi. Okay, and that takes care of the n here. So those are the three restrictions that you would have. You could cross out class example C. We're not going to graph. Last class example is class example number 4. Prove this identity here. Okay, left-hand side versus right-hand side. I'm actually going to start with the more complex side, which is the left-hand side here, and see where I could get this. Whenever you see squareds, I need you to look at your Pythagorean identities. And one of your Pythagorean identities is this guy here. 1 plus the tan squared of x is equal to secant squared of x. Okay, so for this here, what I'm going to do is when I look at this, yes, I'm going to change this into 1 over cos squared of x, but this here, I'm going to change this to an identity. So 1 minus secant squared of x, or sorry, secant squared of x minus 1. I need you to look here and I need you to say, how can I rewrite this in order to get secant squared of x minus 1? And what would that identity be equal to? So if I subtract 1 from both sides, I have the tan squared of x is equal to the secant square root of x minus 1. So this here is equal to the tan square root of x. And for now, I'll just keep this for this first one, secant squared of x. Okay, so I've cleaned up the denominator. Now what I want to do is I want to rewrite these in terms of sine and cosine. So if ever I could get rid of tan, secant, cotan, cosecant, I want to do that. So secant squared of x, what was the identity for secant squared of x? That's the same thing as 1 over the cos squared of x. Tan squared of x is the same thing as sine squared of x over cos squared of x. Let's deal with these two fractions, and instead of dividing, let's multiply by the reciprocal. So the first fraction is 1 over the cos squared of x times the reciprocal of this guy would be cos squared of x over sine squared of x. I hope everyone can see that cos squared of x over cos squared of x would cancel. And what I have here is 1 over the sine squared of x. 1 over the sine squared of x is the exact same thing as cosecant squared of x. If I look at my right-hand side, cosecant squared of x. I don't even have to do anything to that. I mean, I could have rewritten that as 1 over sine squared of x, and then I would stop the left-hand side over here. But because I went to the left-hand side is 1 over sine squared of x is the same thing as cosecant squared of x, I'm actually just going to erase this because I want my left-hand side to be identical to my right-hand side, and what I've done was I've just proven this identity. So left-hand side is equal to right-hand side, and that identity is done. Okay, for the homework questions for this lesson, here's essentially what I want you to do. So number 1, circle that. Number 2, if you want to verify by typing in left-hand side and right-hand side on your calculator, you can. But what I really want you to, like I said, focus on for this lesson is, can you verify and prove identities, and can you find restrictions? So you don't have to do the first part. But what I want you to do for the given questions is prove the identity using an algebraic approach and state any restrictions. I want you to do A for number 2. Number 3, cross out. Number 4, cross out B and D. I want you to do A, C, E, and F. Number 5, don't worry about that. We've done enough restrictions. Number 6, I want you to circle this guy. So essentially, rejig this left-hand side. And if you do this, you're going to get a number over cos of x, and they just want to know what number that is. Okay? And then you don't have to do number 7. That concludes this lesson.